Okay, now let's get started. All right, so I think last time we talked about complete single spaces, what it means to be complete. We gave a definition. We considered some examples of complete and non-complete single spaces. And we explained how to enforce the completeness conditions through simple modification of the left Bowles field localization. And we gave some examples and we proved that the rest nerve is complete, but the ordinary nerve is not. And we proved that the inclusion of the ordinary nerve in the rest nerve is a weak equivalence in the complete single space model structure, using these three observations about the rest nerve. So today, maybe finally, I want to start illustrating the abstract theory with something very, very concretely related to functorial field theory, which is the category of Bordisms. And I'm not going to define the whole category of Bordisms at once. We'll just define one aspect of it right now, and we'll see how to proceed further from there. Okay, so here is a picture for the category of Bordisms that we will find useful. Let me give you some. So, if you recall the first few lectures, we discussed some problems that arise when you try to define a category of Bordisms. And one of those problems was that composing Bordisms is supposed to be given by the gluing operation. But if your manifolds have a geometric structure, such as a Riemannian metric or some other type of geometric structure, it is simply not possible to glue Bordisms in a naive way. If you have two manifolds with a boundary and a Riemannian metric on each, there's absolutely no reason why these two metrics could glue to something, could glue to a metric on the gluing. In fact, it's easy to construct examples where they don't, because, for example, it's easy to ensure that the curvature or the scalar curvature, for example, is not smooth on the gluing. And given that any Riemannian metric has a smooth scalar curvature, it's simply not possible to glue, no matter what you do. So this proves that tricks you deploy in some special cases, like, for example, for ordinary manifolds without any geometric structure, there is a so-called Milnor trick, which proves that yes, we have to make some choices during the gluing process, but the space of such choices is a contractible space. And so the actual choice is not there, so you can organize everything into a nice category. But that's only works for smooth manifolds. Another trick works for two-dimensional surfaces equipped with a conformal structure. And there's something called a conformal welding, which will take care of the job. But again, this is something special for the very special case of two-dimensional conformal structures. And it doesn't work in general. So today, we'll see how the formalism of single spaces allows you to sort of bypass this annoying question of how exactly do the glues get together And of course, this will also require a certain modification of what a bordism is, and this modification can in fact be physically relevant also. So
please may you repeat about how we can avoid this gluing question?
yeah, so that's exactly what I'm going to explain right now. So the you can sort of begin to see it on a picture. The gluing operation will simply, for example, look at two bordisms from 0 to 1 and from 1 to 2, and it will remove this middle cut, which doesn't require any gluing per se, because to specify an object in the Siegel space, you need to specify the whole manifold from 0 to 3, and the cut at 1 will be simply some submanifold. And by discarding the gate of that submanifold, you will you will, so to say, perform the gluing. Yeah, so since I just like a cut, let me define a cut formally. So a cut on a smooth manifold M, so all manifolds are assumed to be smooth. A cut is a triple that partitions your manifold M into 3 parts. Let me maybe draw a picture for you guys. So for example, for the cut at 0, these 3 parts I indicated here will be M less than 0. The cut itself, the codimension 1 submanifold, will be M equals 0. And the remainder will be M greater than 0. So formally speaking, you require that you have a partition of the underlying set of your manifold into 3 subsets. And there should be a function, a smooth function h, called the height function on M, so that 0 is a regular value of h, and these 3 subsets are the pre-images under h of the negative line, 0, and positive ray in the real numbers. So in this picture here, perhaps such a function h could project onto the horizontal axis. So this cut itself projects to 0. And here are the positive numbers, and here are the negative numbers. Yeah, so the idea is that when you glue two bordisms together, well, of course, m equals 0 would be, for example, the source, whereas m less than 0 would indicate to you on which end, so m less than 0 would be the part you were supposed to be gluing. You are supposed to be gluing when you glue this bordism on the left to some other bordism. So in a sense, m less than 0 indicates, for example, the source part that is supposed to be glued to another bordism. Okay, so for a bordism itself, or like in the ordinary sense, you will have two different cuts, 0 and 1, indicating source and target. And in general, as you may know, in a complete Siegel space, the object of n simplices is supposed to be the object of composable n tuples of morphisms. And so in an n simplex, so this picture is in fact a picture of a 3 simplex in an n simplex, you will have n plus 1 cuts numbered from 0 to n. So this is a 3 simplex, is a composition. You think of it as a composable chain of 3 Bordisms as depicted in the picture. And these are numbered from 1 to 3. And an observation to make right now is that there's a natural cut ordering on cuts. So if you have two cuts M and N, you say one cut precedes the other cut if the corresponding subset M less than 0 is a subset of the corresponding subset N less than 0. And likewise, you can write down similar conditions if you want for the other sets, but in principle, it's not necessary because they all imply each other. So in an ordinary Bordism, we will require that the source cut precedes the target cut, which in terms of pictures, so let me draw the corresponding cut here. So this would be M less than 1, M equals 1, M greater than 1. And the condition we impose is that the subset M less than 0 is a subset of the subset M less than 1, which geometrically simply corresponds to saying that the first cut is to the right of the zeroth cut. Okay, so formally speaking, a cut tuple on M is just a sequence of cuts, C0 to Cm, connected by this relation of precedence. So here you see in this picture on the upper left, you see an example of a cut tuple for a 3 simplex. So the cuts are indexed from 0, 0, 1, 2, and 3.
What is the physical meaning of a such cut?
Such cut, you mean what exactly? Sorry.
What is the physical intuition behind of this definition of cut?
Oh, well, the point maybe I should have. Perhaps it makes sense to, well, in a typical this is the same as the usual, motivation for functorial field theory is that, for example, you may think of the Bordism as a space-time. Interesting. So this is a space-time. And the cut itself, you may think maybe perhaps as a space-like slice of the space-time, for example. So in one typical situation, you would have some space, some spatial, some Cauchy surface, if you like, and the space-time would be given by the product of this Cauchy surface and real line. The real line would be your time variable. And that's basically what is called a cylinder on the spatial slice, the Cauchy surface. And this would allow you, for example, to compute the Hamiltonian of your physical system by taking the derivative of the value. So I think I did explain this example before at some time, but maybe.
Yeah, thank you. I understand.
Like this, you have a cylinder of length t, and you evaluate your functorial field theory on the cylinder, and you take the derivative with respect to time t, and you get the Hamiltonian, what is called the Hamiltonian of your physical system that you encode it using a functorial field theory.
And
Yeah, so
cut,
in the first approximation, you should think of the Bordism as maybe some kind of a space-time, or perhaps in some cases, this could be the world volume of a particle or a string. So in the example that encodes quantum mechanics, the quantum mechanics will be encoded by one-dimensional Bordisms. So you will have points and lines, and you think of those lines as the Borg line of a quantum particle. So a quantum particle has its own notion of a proper time, the time of a particle itself, and these Bordisms, so these cylinders will not be real cylinders, but just line segments of length t. And such a line segment will encode the time evolution of your quantum particle for time t. So in string theory, this picture was generalized to two-dimensional surfaces, and then in a two-dimensional surface, you would have a world volume instead of a world line, and which tells you which sort of encodes the evolution of a string in a space time. Yeah. So strictly speaking, in the picture I drew, this would be a picture for a string series. So this would be actually a string. And yeah, this would be the world volume of a string.
in other words, it is a general construction which allow to cover a lot of topics in energy physics. Yes.
Yeah. No, it's you can encode basically quantum mechanics, string theory, and quantum field theory in general. That's the purpose of the construction. So it's all right. Yeah, so a cut tuple is a sequence of cuts ordered in their natural order that we previously defined here. And do notice that a cut tuple, the cuts in a cut tuple are indexed by a simplex. So here we have a cut tuple indexed by an M simplex. And the dependence of the set of cut tuples on a simplex is functorial in the simplex. And so more precisely, if you send simplex M to the set of cut M tuples on M, the resultant set depends functorially on the simplex, or more precisely, contravariantly on the simplex, because phase maps are going to remove a cut, and degeneracy maps will duplicate a cut. I'm guessing a fig here. And this is basically this simplicial structure will ultimately be responsible for implementing composition. All right. Now we are ready to actually define the actual Siegel space. Okay, so let's fix a dimension D greater than or equal to 0. And the category of D-dimensional Bordisms, and when I say category, of course, I don't mean category in the usual sense, but rather I should probably say the Siegel object. The simplicial object in our case, it will be a simplicial object in simplicial sets. The Siegel or complete Siegel space, but this may be misleading, but because the Siegel object we are defining right now is not complete. So it will be a simplicial object, and it sends a simplex M to the nerve of the following category. And let me emphasize, like I said, category here, and not just a groupoid. And this is actually a subtle point that I will have to address a bit later. All right, so what are the objecting morphisms in this category? So objects will be what we call Bordisms. It will be a d-dimensional smooth manifold M. That's what depicted by the total space, by the whole space in this picture. So this whole thing is M. And you need a cut M tuple on M, C. So here we have M equals 3. So we have a cut tuple index by the 3 simplex. So it has 4 cuts index from 0 to 3, 0, 1, 2, 3. All right. And there is one more condition, which is what I call the core of the Bordism, which is simply the intersection. Yeah, and probably I should have also explained this notation. So C greater than or equal to 0. So notice the cuts. Yeah, I should have said the cuts will be numbered from 0 to M. Can I insert maybe some space here? Oh yes, let me insert a bit of space and write down the missing the So C is numbered from 0. So its cuts are numbered from 0 to M. And I'm going to adopt a notation for the generic cut in this cut tuple. I will denote it sets by C less than K, C equals K, and C greater than K. And I will also make applications like C less than or equal to K will be the union. And likewise for greater than or equal to K, and the only requirement I impose here that the core, which is intersection of everything to the right of the zeros cut and everything to the left of the m's cut. So this core is everything in the actual Bordism itself. So it's let me maybe put. So the core will start. I'm sorry, it's probably I should erase some of the stuff. That was Hey, I think this eraser is too huge. How do I decrease its size? I should change the settings. I mean, this. Maybe this. But I thought. Yeah, I'm not sure why the trues are different. Maybe in the settings we can. Yeah, there's only erase true. I don't. Anyway, it doesn't matter. So let me just draw a picture here. So everything between the two light blue lines will be the core. So the core throws away the sort of the flaps and either end of the Bordism. And we require that for a Bordism, the core is compact. And of course, you may ask how physically realistic this assumption is, but in principle, as from what I understood in physics, that's fine. Like, well, for quantum mechanics, of course, that's definitely fine. In string theory, you also assume the world volume to be compact. So it seems to match what you have in physics. Okay, so that finishes the definition of an object in this category. So it's and let me emphasize, of course, this is far from being the final definition. We haven't defined the symmetric monoidal structure of Bordisms. We haven't defined the higher categorical structure, or we haven't introduced any non-trivial geometric structures. So there's a lot more work to do. But at least in the first approximation, the simplest possible example, you now see how this works. And let me also tell you what the morphisms are. So morphisms are what I call cut respecting embeddings of Bordisms. So a morphism between two such objects, so basically two pictures like this one, there'll be an open embedding of the one bordism into the other. So this is an open embedding. And you require that the cuts match perfectly when you map one into the other. So here I expressed it by saying that taking the pre-image of cuts in the target gives you precisely cuts in the source. And furthermore, I require that the image contains the core of the target. So morally, you really just think of you think of this whole thing as encoding basically an isomorphism between two such bordisms. And maybe a typical picture. Let's see, did I draw any pictures here? I'm not even sure what this picture is supposed to illustrate. So these conditions are quite restrictive, in particular requiring that the cuts match perfectly and the image contains the core of the target forces phi to inducing a bijection on cores. So maybe as a remark that even precedes this remark, phi induces or restricts to a bijection on cores. So really the only thing that can change under phi is that these two little flaps little flaps here and here, are allowed to expand under phi. Today is a very colorful, I guess I use so many colors that I cannot even, so many colors. So this little flap can expand under phi. That's the only thing that phi can do for you. Okay, so that's the geometric meaning of phi. It can expand these little germs or colors. Yes, I guess the scientific name for this is a color. But sometimes you will also see the word germ used in this context. So yeah, phi allows the color to expand, but notice something interesting happens at this point, because we take the nerve of this category and we interpret, so these simply show sets, although I didn't really say, but essentially they will be equipped with the Kahn-Quillen model structure, the standard model structure on simply show sets, which encodes infinity groupoids. So you take the nerve of a category and you interpret it as an infinity groupoid. And that's a non-trivial operation, because when you take the nerve of a category, and of course, with these embeddings, you can clearly see that there are plenty of non-invertible morphisms right? If an embedding need not be an isomorphism. And so there are plenty of non-invertible morphisms in this category. And therefore, potentially something very strange can happen when you take the nerve of this category and interpret it as a simplicial set in the Conquilling model structure. In other words, you interpret it as an infinity groupoid, which is a non-trivial operation. So in categorical terms, what happened here is that you took a category and you inverted all morphisms in this category up to homotopy. And in this process, when you invert morphisms in a category, the resulting infinity groupoid can have many non-trivial homotopy groups. It need not be an ordinary one groupoid. It can be can have many higher homotopy groups. And the point of the next remark is to observe or prove that the nerve of the category of Bordisms and embeddings, in fact, is weakly equivalent. So this is a weak equivalence in the Conquilling model structure. So the usual weak equivalence of simplicial sets is weakly equivalent to the nerve of the groupoid with the same objects, where morphisms are now taken to be germs of diffeomorphisms of Bordisms. So the meaning of this is that you take a morphism phi in the sense that was previously defined, and now you identify two such morphisms phi and phi prime if they coincide on some smaller open neighborhood of the core. So if they coincide on some maybe something like this smaller part here. So you are allowed to shrink the domain, and if they coincide, once you shrink the domain, you shrink the color, then you declare them to be equivalent, and you take such equivalence classes of germs of embeddings, and you get a groupoid, because now morphisms will be invertible. And it's a somewhat non-trivial proposition. Yeah. Oh, yeah. We have a comment that if phi restricts to a bijection, I really mean it restricts to a diffeomorphism. Yes, in a sense, but here you have to be careful, and maybe that should be another picture I would have to draw. Well, here's a picture. Here is an example of a Bordism. So here are two cuts. This is the left line is a source cut, and the right line is a target cut. And maybe, well, imagine they wrap around in a circle, for example. So the core of the Bordism would be the black part inside. But do notice the core itself kind of extends in a degenerate way along those lines. So the core need not be any of the familiar objects like, I don't know, like a manifold with corners or anything like that. So it's when you talk about the diffeomorphism of a core, it's a diffeomorphism in what category exactly? And it's you can say maybe restricts to a bijection on restricts to a diffeomorphism on germs, of course, maybe some arbitrarily small open neighborhoods, of course. And of course, it also restricts to a diffeomorphism on the interior of the cores. So yeah, so of course there are tons of diffeomorphisms hanging around, but the phi itself, it's a bit difficult to say what it means for phi to be a diffeomorphism in the first place, because the cores are themselves just compact. They are compact topological spaces, but they don't have a nice local model like a manifold. So you have to be careful. But in a sense, you could say it's a diffeomorphism in a sense that phi, of course, restricts to a diffeomorphism on open neighborhoods. So maybe that's what I should mention here. It's a bijection and also a diffeomorphism in a precisely defined sense that it becomes a diffeomorphism once you extend it to a small open neighborhood. All right, so that completes our definition of the most elementary possible Bordism category. So maybe it's time to ask if you guys have any questions at this point.
For what reason we take the nerve of cats of Barangism, or what is the intuition behind all this?
So again, the nerve of what?
Of cats.
Which paths are you talking about here? Sorry.
The remark is right. Right.
The nerve of the
Cat,
yeah, I
nerve.
mean the intuitive geometric meaning of this remark is that once you start inverting embeddings, well, I mean maybe you should maybe I should draw a picture. So here's maybe a picture that will explain at least some of the. I mean, how can we see that after such process, we only see the germs of diffeomorphisms? Uh, so let's say we have. Yeah, let's say we have two such diffeomorphisms, two such embeddings that have the same germ around the core. So let me draw a picture. Let me draw the simplest possible pictures, like cylinders. So here are two bordisms that look like cylinders. And let's say we have two maps, phi 1 and phi 2. And let's say phi 1 and phi 2 coincide as maps in the ordinary sense on some smaller open neighborhood here and here. And but phi 1 and phi 2 need not be equal in general. Well, how can we see that? In the when we take the nerve of the category of embeddings, phi 1 and phi 2 will be equal. Well, that's really easy because you can simply say um, here is let's construct a similar cylinder, but let's now shrink the color physically. I mean, and let's do something relatively small, like this. And now the on this smaller neighborhood, which matches what we had here. I guess the blue is not very distinguished from red, so maybe. So phi 1 and phi 2 will restrict to the same common phi here. Let me call it psi maybe. And so in formulas, phi 1 composed with psi equals phi 2 composed with psi. Because psi lands entirely within, so this tiny neighborhood, this entire tiny neighborhood lands entirely within this neighborhood where phi 1 and phi 2 coincide. So when you pass the nerve of this category of embeddings, all three morphisms will be forced to become invertible. So in particular, since psi is now invertible, you can say, okay, so in the nerve of the category of embeddings, psi is invertible up to homotopy. So this is a nerve in the conquilling, entropic in the conquilling model structure is invertible. And therefore, the equality of phi 1 composed with psi, so this is an equality in the usual sense, like just two embeddings coincide, implies that we can compose with psi. Now remember, in a quasi-category or in a concomplex, both the inverse map and the composition is defined only up to some contractible choice. So here I will no longer be able to say equals, but only homotropic. Oh yeah, this is not phi, this is psi. So we can make a choice of psi inverse. We can then make choices of these compositions here. And finally, we can observe that psi composed with psi inverse, of course, is homotropic to phi 2 and homotropic to phi 1, respectively. So you see, with this trick and the fact that all morphisms, all embeddings are inverted up to homotropy, it forces magically forces everything to become just a germ of a diffeomorphism. Okay, more questions? Oh, yeah, so maybe we should connect this to the example last time. So last time we had examples of encoding categories of spans and co-spans. In principle, the construction we just wrote could be interpreted to some extent as a category of co-spans. I mean, in fact, that's a very reasonable interpretation, not from a practical viewpoint, but maybe from the point of intuition, is perfectly fine. So maybe I should say very quickly Bordisms as co-spans. So here's maybe a let's see. So let's say we want to compose. So here is one Bordism. And yeah, so how do we interpret such a Bordism as a co-span? Well, I already mentioned that for geometric structures, you need not just a codimension one manifold, but an open neighborhood of this codimension one manifold. So you really do need a color to be present. So this could be interpreted as a co-span of colors. Let me draw a picture as best as I can. So here's a picture of a color. Yeah. And this color embeds here. And likewise, here's a picture of a color here. Embeds here. And you can do, say, yeah, so in our case, a Bordism would correspond to a co-span where all objects involved in the co-span have the same dimension. The same dimension D, and morphisms in the co-span will be open embeddings. So both legs of a co-span are embeddings of D-dimensional manifolds. And now, of course, you can try to compose two such co-spans. So let me maybe put another example, another Bordism here. And of course, let's say the colors here are small enough for this to be also embeddable here. And here we have some I'm sorry, I'm really bad at drawing colors, but yeah. Okay, now you could say, oh yes, we should just, with those colors present, we can just compose these guys as co-spans, and the composition should be the gluing. And in principle, this can work if you are careful enough and aware of several pitfalls that can arise when you try to make this precise. And I should probably mention at this point that this is very much the approach of Stolz and Teichner. I mean, they may not have used the word co-span, but it's very much what they do. So if you read their, I think it's 2012 survey, but even before that, well, I guess the 2012 survey is the most detailed, or is it 2011? I always forget. Has the most detailed exposition, and there they do explain how to make this precise. So what are some of the pitfalls I mentioned? Well, one thing is that if you are not careful enough, and if you just start gluing by taking the push out of this, the resulting manifold need not be Hausdorff, because let's see. Let me maybe draw another picture just to illustrate the problem. And let me draw the stupidest and simplest possible picture. So here is our codimension 1. Guys, here is our neighborhoods. And here is our true embeddings. And what kind of problems can arise? So when we take the push out, well, one problematic thing is that potentially it is, well, imagine the actual bordism is somewhere here. Maybe I should have at least extended to the actual bordism. And there's another actual bordism somewhere here. So you're trying to glue some bordism that comes in from the left and extends all the way to this codimension 1 submanifold, and another bordism that comes in from the right. So here's some bordism maybe here, and extends to this codimension 1 submanifold. And you can, if you look carefully, you can see a potential problem that, yeah, you say, oh yes, this open neighborhood of the codimension 1 thing is what we want to identify on both sides. But notice, for example, it is possible a priori to have a point, which I depicted in red here. The red point need not be in the image of this embedding. A priori, there is nothing that will force it to be in the image here. And likewise, on this side, you can also have some points on the color that will not be in the image. And of course, this is problematic because the red point, well, let me only erase this. The red point is supposed to be glued to the red point here. But, right, these 2 points must be identified. And this is not going to happen unless the red point is also present somewhere here. So if there is a green point that maps to the red point, then the green point will map to the red point here. Maybe I should also make it red. But this red point need not exist if the color here is too small. So, and this problem, so to say, has some solutions. And one maybe very simple solution is to not look at arbitrary spans, but imposing additional condition on the span. Let me see if I can formulate this condition correctly. So here is so let's look at the span. This object is given by some cut in our terminology. And this bordism here itself has a cut at this point. And one thing that we can require to sort of force a quick fix to this problem is to require that m less than 0 is maps to b less than 0 diffeomorphically. So in other words, this color here must be precisely as big as the color here on the left, so the left part only, not the whole color, but the left part only. So in particular, this type of condition will force the red point here to always have a pre-image inside the color with respect to which we glue. So this type of restriction can, in principle, at least deal with this problem. Then, of course, you also need to take into account, just like we did previously, you need to take into account the fact that germs must be allowed to shrink. So this will add another layer of complication. So in principle, yes, it is possible to treat the definition. The elementary definition can be mutated into the setting. And to answer the new question in the comments, so the question asks whether the cospan construction is insufficient because the push-out does not necessarily exist. Yeah, so that's exactly the point. So the conditions we are imposing here, like the red condition that I just imposed here, this condition essentially guarantees that the push-out exists in the category of smooth manifolds. So, or more precisely, in the category of smooth Hausdorff and paracompact manifolds. So in particular, Hausdorff can be a problem unless you impose this condition. And of course, you also correctly pointed out in the comments, Alex, I mean, that if you have a geometric structure, then you immediately have more problems, right? More problems because now you also have to say how the geometric structure glues. And of course, it glues, but it glues only up to homotopy in general. So now you have a new problem to solve, and you can either say, okay, let me develop some homotopy coherent formalism to handle this gluing up to homotopy, which is possible. I mean, it's not a problem, but it will be roughly as complicated as a Siegel space now formalism. The other trick you could deploy is you could say, oh, I'm going to deal only with pre-sheaves that admit a strict gluing. So what you could say is, okay, I'm going to take my simplicial pre-sheaf, and I'm going to require that this simplicial pre-sheaf is fibrant in the injective model structure, for example. This guarantees that gluing is always possible to glue strictly. And in principle, you could also go this route, but you still have to deal with the problem that the gluing need not be unique. So in principle, most of the other problems still remain, and it's not going to resolve your main issues. So in principle, all those issues produce roughly similar problems. Yeah, so yeah, to comment on the other part of this comment, yeah, so we do circumvent the issue of composition by sort of postulating the composition in advance, and then so we require that only stuff that can be glued is gluable. Yeah, so then gluing just amounts to removing the middle. Removing the middle cut in this picture, and that's zero gluing. Yeah. So that's a perfectly legitimate way to solve such problems. Yes. What about next question? What about additional conditions on the definition of a cut inspired by the main image? Yes. So to answer the first question, it is possible. Where is a picture? Yeah. So of course, here I could have said just as well that you can also say you can add non-script ones here, but perhaps even more importantly, yes, the question asks whether it is possible to maybe perhaps postulate a condition like maybe I can turn this into a nice little remark. Somewhere here, yes, somewhere here. As a little remark, we can also require, oops. In the ordering on cuts, we can also require that, for example, C at most 0 is a subset of C less than 1. So in practice, so notice the true sides have different strictness, non-strictness. So in particular, the new part here is that the cut itself is a subset of C less than 1, which means that the true cuts must precede each other strictly. So here is so this part is a C less than 1, and so I require that C equals 0 is strictly to the left of C equals 1. So in particular, C equals 0 is disjoint from C equals 1. Which means that the pathological examples, for example, what we disallow, this condition disallows, say, examples I previously mentioned to you where you would have a true cuts C0 and C1 that precede C0 precedes C1, but they do have an overlap. So this is not disallowed. So what can we say about such a Bordism category? Yes, it is possible to require this. At this point, we should probably still consider it to be problematic because if we do impose such a condition, then, for example, identity Bordisms become problematic because identity Bordisms are simply given by applying the simplicial degeneration map. So you start with some cut, and you simply duplicate this cut, so you now have two identical cuts. And they coincide, they overlap everywhere, so of course this stricter condition is not going to be satisfied. Identity Bordisms are problematic. But even more importantly, perhaps for quantum mechanics, for example, in the definition of the Hamiltonian, we require that we evaluate our functorial field theory on an interval of length t, and we take a derivative as t approaches 0. We take the derivative, so we need to take the derivative at t equals 0. And of course, this definition would disallow t equals 0, so this would not be possible. So maybe as practical considerations from physics prevent us from imposing such a requirement right away. In principle, the problems that we identified here can be alleviated to some extent by adding isotropies. So this is something we haven't discussed here, but adding isotropies partially resolves the problem. So what are the isotropies? Well, isotropies are, you may have heard in the ordinary cobordism hypothesis, you want to encode not just diffeomorphisms of bordisms, but the whole homotropic type of the group of diffeomorphisms. And this is what isotropies correspond to. So isotropies in particular will add higher morphisms to your categories that basically allow you to take an endpoint here and move it to some other arbitrary point on the interval, with the result being homotropic to the original bordism. And notice that such movement seems to decrease the length of the interval, but that's not a problem because the homotopy itself is going to have its own intrinsic notion of length. So the length doesn't disappear, it just is relocated to the homotopy. And this would at least resolve the problem partially because now in the new category with isotropies, we have identities up to have identity bordisms up to homotropy. Or up to, more precisely, up to isotropy. And the resulting theory, at least in the formal categorical sense, will be equivalent. So the theory of infinity n categories with that have units up to homotropy is equivalent to the original category. So in principle, it's not a problem that you are not going to have strict identities. And notice this is also exactly how you handle identity bordisms in the setting of traditional topological field theory. Because in a traditional topological field theory, you say, oh, a cylinder on some bordism, on some manifold M, a cylinder will be an identity bordism. And that's exactly what we are saying here, that an identity bordism up to isotropy, well, that's just a cylinder, a non-trivial cylinder on your object. And an isotropy allows you to move the endpoint, the end cut of the cylinder. You can move it to the source cut and get an identity in this manner, so to say. And this would be a sort of a relatively close match to the identity bordism in topological field theory. So why we decided to allow this more general bordisms? Well, it's mostly a matter of convenience, because we do want identities in the usual normal sense, And perhaps we do want to define a Hamiltonian using a very intuitive and simple family of Bordisms. And this, of course, will still be possible in the other setting. As I said, the true series will be completely equivalent. So in the absence of those degenerate Bordisms, but in the presence of isotropies, it is possible to prove that the resulting notion of a functorial field theory will be exactly the same as before. Functorial field series in the new sense will be the same as in the old sense. So in principle, there is no serious difference. It's only a difference in the level of convenience and in the level of intuitive explanations available to you.
Okay, thank you.
Yeah, you're welcome. Oh, there's one more question. What happens if the colors are connected? Well, that's not always possible because imagine, already for this Bordism here, where is this? Oh yeah, so maybe I should have said, oh yeah, this picture here, right? So the colors are not, so here, this is like m less than 0, right? This part, and this is not connected. So it's not connected, so it's not going to be a connected component. Or maybe you're meant to say, yeah, I'm not sure what this question is trying to ask. But if you just require this to be connected, then you would disallow such Bordisms. Yeah. All right, more questions? Okay, so let me maybe just mention a few more things we will have to take care of in the future. So some aspects that haven't been treated yet, and I think it is at least like 5, right? So first of all, we do want not just, so here as you can see, I defined an ordinary category, more precisely an ordinary infinity 1 category, a single object in groupoids, basically, or more precisely categories, but these categories are weakly equivalent to groupoids. And we really do want a D category, or more precisely infinity D category of Bordisms. So Bordisms, we should also be able to cut and compose them in all possible directions. And this will not be particularly difficult to handle. I mean, this, of course, will require replacing D with the Cartesian power of D. Delta, the category that controls composition, will have to be replaced with a D-fold Cartesian product of delta. So that's what is called an n-fold Siegel space. Of course, we also want a symmetric monoidal structure. So this will require something called gamma objects, which are very, very similar in spirit to delta that we previously studied. It's just a slight modification, very similar in spirit. So this will not require any new insights from you. Okay. Then we'll need geometric structures in Bordisms, like I previously mentioned. And this will require us to say a few more things about simplicial P-sheaves and how they work, and stacks in general. We also want to be able to treat smooth families of Bordisms, and part 4 is actually crucial when I mentioned to you that to define the Hamiltonian, of a physical system, you will evaluate your functorial field theory on a cylinder or interval of length t, and then check the derivative as t goes to 0, at t equals 0. And of course, to be able to check the derivative, you must require that change in t smoothly produces a smooth family. And there is absolutely no reason why it should produce a smooth family. So that must be imposed manually, and that's what part 4 is about. It will impose this condition manually. And finally, I already mentioned also isotropies to you. Isotropies, well, we don't need them to ensure identity bordisms, but they are still necessary for exactly the same reason that you need them in the geometric cobordism hypothesis. And one of those reasons, of course, is that among many other things, these isotropies will make bordisms dualizable. And dualizability is of course crucial to the cobordism hypothesis, right? So without dualizability, you have no chance of proving GCH. So there's still some things to handle for us. I mean, but at least the first two parts we are very much familiar with because we know what Siegel spaces are now, and generalizing this to the n-fold case is really a formality, and gamma objects are only slightly different. Yeah, geometric structures and smooth families will require us to talk a bit more about sites and simplicial presheaves and all that stuff with Czech localization and whatever. And finally, isotropies will add at the very end, and they will fit nicely into the existing formalism. They will not require a substantial change in the formalism. The only part I will want to change, we will have to inject smooth sets at this stage into the construction. So this will be a mild addition to the formalism, which is not particularly serious. Yep. So that's the overview of the future, maybe 2 or 3 lectures. So, and once we are done with this, we will be able to define the ultimate all-encompassing bordism category, which will take care of the entire definition. And at this point, we will have the correct definition of a functorial field theory. And we will be able to immediately formulate the geometric cobordism hypothesis. Yeah, so we are maybe 2 or 3 lectures away from the GCH per se. Maybe a bit more, maybe like 4 lectures, but in March, definitely in March, we will be able to say what GCH is and how it works. So I hope the long wait is coming to an end. We started mid-October. It's exactly like a German semester for us, I guess, because in Germany, semesters also start in mid-October, I think, and then they go through the Christmas with a little vacation during Christmas, and I think you end like in February, right? In February, you would end the semester more or less, yeah. So maybe it's even a bit longer than a semester-long course, but whatever. We only meet once a week, so that's a big difference. Also, German universities don't work on Sundays for sure. All right. Any more questions for today? Because I think this will be a good time to stop because it's 10:26. So I doubt I should start the new topics. The new topic, of course, will be gamma spaces, but it's maybe something for the next time. Any more questions, guys? Okay, then I guess I'll see you guys next week, and have a nice rest of the Sunday, I guess. Yeah. Uh, Did you guys already decide whether it will be a paper? Yes, we did decide affirmatively. So we are preparing a separate paper in geometric structures. In fact, that's exactly what I'm working on as my research right now. So to finish this paper, yeah. It should be ready maybe. Oh yeah.
I have one question in chat.
Oh yeah, sorry. Can your definition be extended to the infinity category of Bordisms? Yes, I mean it won't be a problem. I mean if you want, you can of course. Well, okay, there is a bit of a problem because in the current definition we fix a top dimension d, and you're required to have so all k morphisms from 0 to d are required to have d-dimensional germs. And I wouldn't really say that the topological infinity category of Bordisms is well known, because it's like, yes, somebody mentions somebody somewhere on in some comment, but is there an actual write-up? Not to mention a published and refereed write-up. Of course not. So it's like, yeah, somebody left a comment somewhere doesn't mean it's well known. So it's more like, yeah, we have some potential example in mind, which would sense to maybe write up. I know this would be a good master's thesis. If you want, if you have a master's student, you can offer this project to him as a project. But it hasn't been done yet, and for geometric structures, somewhat, well, this would require noticeable modifications, at least to our formalism with geometric structures. We would require to introduce a notion of a stable geometric structure, which is a geometric structure that you can promote from dimension d to dimension d plus 1. And in principle, we do have some ideas how to do that. So this will be a further layer of complication added to the theory. In principle, that's something it is possible to do, I would say, but it will be a new ingredient in the construction. Yeah. So if you, I mean, probably writing up a Jessica definition will no longer be, well, Kovak and Scheinbauer wrote their note on Jessica definition of a infinity n category of Bordisms, and they only get the topological case. That was already publishable in Algebraic and Geometric Topology, and which is a top specialist journal in algebraic topology. So yeah, whatever. Maybe you can assign this as a master thesis, and it will be a very, very good quality master thesis. Yeah.
Is it possible to generalize a single space in this case for such category, general category, infinity categories? Also?
Yes, I'm pretty sure, yes, it is possible. In fact, if you read this question on mass overflow, they do indicate some, I'm pretty sure they indicate, I mean, basically, there are ways to construct infinity categories from various models from infinity n categories. And if you go to this, that's just, by the way, that's not the only answer. This is a fairly old answer. I'm pretty sure I can point you to a couple more recent answers about infinity category. And now there are also papers. I'm pretty sure, like, I think Lubaton had a paper that's recently, or was it him or not him, who had a paper in infinity categories. So just this year, or maybe the last year, there was a paper on infinity categories. So if you cannot find it, you can ask me. I'll find it and email it to you guys. So there are papers now. Infinity categories is just that they haven't yet constructed any seriously non-trivial examples of infinity, but we do have theoretical papers now. Yeah.
And as I understand, they in this paper generalized single spaces, yes, for encoding this definition.
I'm not sure about the specific concrete model. Could be single spaces. I honestly didn't look very careful inside, so I don't really know. But could be single spaces, could be completio sets, which is another model. So I'm not totally sure what exactly was in that paper, but yeah. So notice also there are at least two different notions of infinity category. One uses basically a limit, and the other one a co-limit of the diagram of infinity n categories. So they differ, and they have very different properties. So keep this in mind.
Thank
Yeah.
you.
Okay, more questions? All right, if not, I'll see you guys next week, or maybe some of you at the seminar, maybe all of you at the seminar, because I think that there's now a 100 containment relation between participants here and participants in the seminar. So maybe I'll see you all guys even earlier than Sunday.
Will there be any talk on Tuesday on geometry and topology seminar?
Let me see. So the schedule is actually posted online. Let me just give you a page. I don't think we scheduled anybody yet, so so this page contains the up-to-date schedule, and I see that we have Luigi Alfonsi on March 19th and Paul Stevens on March 26th. We haven't scheduled anybody yet for yeah, so I guess February 20th most likely there will be no talk. Maybe somebody will still ask for February 27th or March 5th. So we'll see.
Do you know if Luigi will talk about his paper on BV formalism?
I would expect so. He has yet to send me a triconing abstract, so we'll see what. I usually don't restrict people, so, but that's my expectation at least. So yeah, and Bill and Stevens probably will talk about something about derived C infinity, derived smooth manifolds, derived differential geometry. So yeah, so they both have related topics, I guess. And we also asked a bunch of other people. I'm still asking new speakers to talk, so this is not a final list for this semester. Yeah.
Okay, great. Thanks for the talk.
Yeah, you're welcome.
Bye-bye.
Okay, bye.
You-
See you guys next week.